So today we will cover three different topics. In the first video, I will talk about asymmetric loading a little bit more. So we'll have continued discussion on asymmetric loading. And then in the second topic, I will talk about general eccentric loading. So in general eccentric loading, we're gonna have normal force N, and we're gonna have M that is not on the principal axis. That will be the case we're gonna discuss. And as a third topic, as always, we'll talk about stress concentration. And we somehow went through similar logic in the torsion chapter and in the normal loading chapter, right? After discussing everything, we finally discuss about stress concentration, which is very important to design mechanically reliable structures. Okay, so let's begin from the first topic. Continued discussion on asymmetric loading. So in previous lecture, I told you that we cannot find principal axis for general complex cross-sectional shape because it involves like a linear algebra and eigenvalue and eigenvector calculation. However, if we limit our focus on rather symmetric cross-section, we can find it quite easily. And so let me make a short comment on that. And even though I'm not gonna tell you like details of mathematics, I will try to introduce how we can approach the problem for general complex cross sections. Then I will try to solve one example problem considering symmetric shape. So regarding the symmetric shape, the shape such as this, when I say symmetric shape, I mean a shape having two planes of symmetry. Okay, so if you have like a quite symmetric shape with two planes of symmetry, and what you can do is you first take the centroid position as the origin, and you try to take like a one plane of symmetry. Okay, and after you take this one plane of symmetry and you just to take another axis, and that is it. Okay, then this will give you the principal axis, and because these axes went through the centroid point, we call that as principal centroid axis. Okay, so when you think about why it satisfies this condition, you can see that in this section, y multiplied by g will have positive sign. If you consider that section, what you can see here is you're gonna have negative g and positive y, but so that it will have a negative sign. But you can see that this section and that section are identical in shape, so that they would be cancelled out during this integral. It's same for the other sections. So when you have positive g and negative y, you're gonna have negative sign here. You have negative and negative g, you're gonna have positive sign of yg multiplication. However, they have same shape and in same area, so you're gonna see that they're gonna cancel out here, so that you can quite easily see that if you take out central point and try to positioning two axes in this way, you will be able to satisfy the condition for principal axis. Now regarding the complex like asymmetric shape, general shape, of course you can do that, but there is mathematical way. This is not super serious. You can for any engineering student who have taken linear algebra can do this, but because most of you haven't taken the linear algebra course yet, so I'm not gonna get to the detail. But what you do is quite simple. So you take any arbitrary axis y prime and g prime, then you construct 2x2 matrix. 2x2 matrix composed of gg component, yy component, and yg and yg component. You construct a symmetric matrix out of these three component of area moment of inertia, four component of area moment of inertia, and you just simply obtain the eigenvectors. Okay, then what you're gonna see here is you're gonna find that that component and that component too will be equal to each other, so that it's a symmetric matrix. And for symmetric matrix, you are guaranteed to have two real eigenvalues, and you are guaranteed to have two orthogonal eigenvectors, such that you are always guaranteed to have two principal axes for any general shape, okay, regardless of complexity of shape. This is what you're gonna get, based on you are guaranteed to have two orthogonal principal axes, um, yeah from the linear algebra, okay. However, because this is beyond the scope of ME tutorial, we're not going to discuss about obtaining principal centroid axis for general asymmetric shape, okay. So so let's stop our discussion here, and let's try to solve some real problem. So the problem we're going to consider is instead of having m only in z-axis, we can have moment vector in this way, like so the moment vector has like angle theta with the horizontal axis. Then what you can do is, because m is basically torque, and because m is torque, you can decompose torque into two different orthogonal vector part. So you can decompose the problem into mg and my problem, okay. So after decomposing original problem into first mg problem, second my problem, then you can solve any kind of problems, given that you have the principal axis information. And as I told you, for this symmetric shape, principal axis is really easy to find, right? So regarding the first problem, this is the problem that we already have answered. So we have our flexure formula. So the reason why we have a negative sign is that because mg acts in this way, so that when y is positive, I mean this upper direction, due to this mg, if you think about your right hand row, you can see that there's going to be compression and there's going to be tension, and we set tension as positive sign and compression as negative sign. We have to have, when y is positive, the stress must be negative or compressive, okay. So this is how you set how you obtain sigma x. Of course, Ig and mg can be obtained from simple vector relationship, because moment is vector and you can use the vector decomposition rule. And Ig, this is the definition we have went through in previous 4 lectures. And regarding the second problem, the only confusion is you have m in different direction. However, the principle is the same. But here the thing you have to be careful is, when you consider my pointing in positive y direction, if you think about like a right hand row, you can see that there's going to be compression in right side, and there's going to be tension in left side. Because we want to have a positive sign for tension, you got to be careful having a positive sign for sigma x, okay. Other than that, these two equations are mathematically analogous, okay. Instead of mg, you have to put my. Instead of y, you have to put g, because my is locating here. And instead of ig, you have to use iy, and iy is defined for having g equals 0 as the center, and you do this integral, then you can obtain iy, okay. Of course, my you can simply obtain from vector decomposition. From m, you take sine part, and it'll be my. Then by combining these two answers, sigma x can be written as function of both y and g position, minus y over ig mg plus g over iy multiplied by my. This is the final answer. Then people can ask, where is neutral plane? And it's quite easy. You simply find sigma x equals to be a 0 condition, and from 0 equals to be this secant condition, what you're gonna get is y equals to be ig over iy. Actually, this tangent comes from my over mg, okay, and multiplied by g after massaging these equations, okay. And where did you get this tangent theta? My is m sine theta, mg is m cosine theta, and that's why this ratio becomes tan theta, okay. And we call this as the slope of y equals something z line, and let's say that this is tangent phi. And if we define these number as tangent phi, From this linear relationship between y and z, you can immediately figure out that actually, this is the angle between the horizontal axis and the neutral axis, or sigma x equals to be 0 position, the neutral plane, and you can identify that this is the angle between neutral plane and the horizontal plane. Okay, so this is quite interesting. Until now, when we apply moment m vector always went through the neutral plane. However, for this asymmetric loading problem, please don't confuse that. We are doing asymmetric loading over asymmetric cross section. We are doing asymmetric loading for symmetric cross section. Okay, so for most general cases, when m is not parallel to the principal axis, what you can expect is m will not go through the neutral plane. And of course, we can obtain the condition when the m went through the neutral plane. It went through neutral plane only if theta is 0 or 90 degree. So that this is 0 or 90 degree. Then you can see that it'll in the phi and theta will be identical number. Okay, or when iz and iy are equal to each other, even though it's not I would say, even though your shape is not exactly supersymmetric shape, you can have two integrals happen to be equal to each other. Okay, so other than these two cases, you can expect that your moment vector m and the neutral plane will not correspond to each other. Okay, so that's the lesson about asymmetric loading. And as I told you, because we don't have linear algebra yet, we're not going to consider asymmetric cross-sectional shape. We'll consider symmetric cross-sectional shape, but still we can consider asymmetric loading, asymmetric bending deformation. Okay, and for such asymmetric bending deformation, then moment vector is likely to be not on the neutral plane. Okay, so with that, let me finish my first lecture of today.